Hi everyone. Today we will be talking about two very cool mustaches from the 20th century. Bear with me. And how they help us in freediving. But first, let's talk about hemoglobin. Hemoglobin, from the Greek word hema for blood, the Latin globus for ball or sphere, and in for protein, is, you guessed it, a protein. It is present in red blood cells. It contains iron, also known as a metalloprotein, and importantly for us, transports oxygen. It is found in all vertebrates, except for these guys, and carries oxygen from the respiratory organs, for us still the lungs and not gills, to the rest of the body. At the tissues, it releases its oxygen to allow for aerobic respiration to take place for metabolism. A healthy individual human has 12 to 20 grams of hemoglobin in every 100 ml of blood. It also carries 20 to 25% of our body's respiratory CO2 and carries nitric oxide that it releases as oxygen. Isn't hemoglobin great? Now, let's move on to those cool mustaches. I present you with Christian Bohr and John Haldane. Who has the most epic mustache? We have to give it to Haldane. That thing looks like it has a mind of its own and is taking Haldane for a ride. But how do these two mustaches help us freedive? Let's see. Christian Harold Lauritz Peter Emil Bohr, who lost the mustache comb but made a comeback with that name, was a Danish physician with some pretty strong genes. He was the father to physicist Niels Bohr and grandfather to yet another physicist, Age Bohr, both of whom won Nobel Prizes. But more importantly for us, he described the Bohr effect, in which hemoglobin's oxygen-binding affinity is inversely related both to the acidity and to the concentration of carbon dioxide. This was the original graph that he used. But let's break this down. An increase of CO2 results in a lowering of the pH of our blood, meaning that our blood becomes more acidic. Low pH is acidic and high pH is alkaline or basic. This in turn causes the hemoglobin to release its load of oxygen. Each hemoglobin molecule can carry 4 oxygen molecules. So the Bohr effect facilitates oxygen release when CO2 is elevated. After hemoglobin picks up the O2 from the lungs, it can release it where it is needed. Now let's look at Haldane. John Scott Haldane was a British physician, physiologist, and philosopher, famous for experimenting on himself and his son, I blame the mustache, by getting in sealed chambers and breathing potentially lethal cocktails of gases while recording their effect on his mind and body. That may seem crazy, but he actually made some very important discoveries about the human body and the nature of gases. And he created the first reliable decompression tables for diving, which are still used today. Let's look at the Haldane effect then. This is a property of hemoglobin within which oxygenation of blood in the lungs displaces carbon dioxide from hemoglobin, increasing the removal of carbon dioxide. What this means is that, in simple terms, the lower the O2 in hemoglobin is, the more CO2 it can carry. So, a hemoglobin molecule that has taken fresh O2 from the lungs and delivered it to the tissues and is now deoxygenated can, thanks to our friend John Evil Mustache Haldane, carry more CO2 back to the lungs. In detail, how this works is the following. When hemoglobin has no bound oxygen or carbon dioxide, it has its unbound shape. the binding of the first oxygen molecule changes its shape to one that increases its ability to bind to the other three oxygen molecules. This takes place in the lungs. As we mentioned earlier, with dissolved carbon dioxide, the pH of blood changes. This causes another change in the shape of hemoglobin, which increases its ability to bind carbon dioxide and decreases its ability to bind oxygen. This shape-changing process continues with the oxygen bound to hemoglobin being released into the blood's plasma and absorbed into the tissues, Bohr, and the carbon dioxide in the tissues being bound to hemoglobin, Haldane. In the lungs, the reverse of this process takes place. With the loss of the first carbon dioxide molecule, the shape again changes and makes it easier to release the other three carbon dioxide molecules, and so on. In summary, you see that together, these two effects illustrate our body's ability to efficiently transport more O2 where it's needed and more CO2 from where it's not needed back to the lungs to be offloaded, and how these two mechanisms help protect us and the balance of our gases when freediving. Perhaps this is something to consider when we mess with our natural gas levels during our breathe-up before diving. And that's it. We went from 20th century self-experimenting evil mustaches to the intricate journey of oxygen and carbon dioxide on board the awesome molecule of hemoglobin. I hope you found the video interesting. Thanks for watching and see you next time.